Hello everyone, my name is Anthony Correa, and I'll be presenting on the identification of star clusters in merging dwarf galaxies. So a little background on dwarf galaxies. Dwarf galaxies, as said in the name, are smaller in size in comparison to large galaxies such as the Milky Way. They have an environment and contain properties that are similar to galaxies of the early universe, which is what makes them so interesting and unique. However, the information and understanding we have of dwarf galaxies is very limited, even more so for merging dwarf galaxies. And so what you see on the right is an image of the galaxies I chose to work with and analyze over the past few weeks, known as DM0944 for me. As shown by the key, these galaxies have a radial separation of roughly 10 kiloparsecs and a velocity separation of 10 kilometers a second. Down in the bottom right identifies that the distance shown are 20 arcseconds, which is equivalent to a distance of 2 kiloparsecs. But this is just to give you a rough idea on the distance between both galaxies. So, over the course of the summer, I would install code and prepare programs astronomers used to analyze their images. Here is an image of the same galaxy after running it through an RGB code. To sum it up, pictures of the galaxy were taken through 3 different lenses or filters. The I band captures the red end of the optical spectrum and shows older stars. The H alpha filter captures the emission of newly forming stars, and the U band captures the blue end of the optical spectrum and shows a broader range of young stars that H alpha captures. I assigned each filter with a color. The I band was assigned red, U band blue, H alpha green, respectively. Once each filter was assigned a color, I would layer them one on top of another and fine-tune the parameters to make the image you see before you. And so, the RGB image that contains 3 different layers of filters, represented in its own unique color, can help us make some interesting observations. We'll begin with the galaxy located on the upper right. We can see from this image alone that the galaxy is shaped irregularly, and it has this incredibly interesting meandering shape. Furthermore, we see select concentrated areas of newly formed stars surrounded by a magenta reddish hue. So the newly formed stars are surrounded by older stars. This galaxy, which was located on the left, looks to be spread out, diffused, and overall more open. We can see that there are fewer older stars, as seen with the lack of red. But similar to the other galaxy, there are small concentrations of newly forming clusters. And as the galaxies flow to one another, the gravitational force begins to manipulate the structure of the star clusters, and they begin to merge. And real quick, the newly forming clusters would be the very bright circles that you see in the images, in these 2 images. Moving on. Mergers occur when 2 galaxies collide with one another. A merger is considered a major merger when both galaxies are of the relative size and mass. A merger is considered a minor merger when one galaxy is vastly larger than the other and just simply absorbs a smaller galaxy as they collide. Technically speaking, we're observing a major merger, even though it's between 2 dwarf galaxies, which is significantly smaller than 2 large galaxies colliding. As galaxies merge into one, they spread dust and gas in all directions, which lead to starbursts. And here's a simplified graph that can give you a rough idea of star formation rates during and after the merger process. The main sequence shows star formation that regularly happens in galaxies, as identified by the blue trend line. Starbursts, represented by the pink trend line, occur from mergers and have a star formation that is higher than the main sequence. And the interesting thing about this when applying it to our galaxies is that our galaxies have an unusually high number of star clusters to begin with. Being able to find out what happens post-merger is something we'd have to find out through simulations. But that is looking far down the future, because the ability to create accurate simulations all depend on the information we can collect right now, as well as the limitations of technology. But it all starts here. And what we have here are 2 of the same images. However, the image on the right is the product of running a star finder code. Don't worry about the axis, it just means that the image is 4000 by 4000 pixels. So the code works by finding the mean, median, and standard deviation of the background by clipping out the stars. We then have the computer identify sources that are 5 times the value of their standard deviation, with the center of detected sources to be within 3 pixels. We end up identifying roughly 32,800 stars in just this single image. Once I identified these sources, I used circular aperture to help visualize the data collected, which led us to the image on the right. And if you compare both images, you can see that where the galaxies are located, the image on the right has a much denser population of circular apertures. So, once the stars have been identified, I created a table that shows the location of each star and their respective aperture sum. Here, I only show the values of the first 3 identified clusters, or the first 3 identified stars, rather than the whole bunch. The concept of this program will be considerably useful when we start identifying star clusters, because the goal is to identify star clusters within and nearby both dwarf galaxies and have a number in the hundreds region. Once we find the correct parameters, creating a table like this one will help locate each star cluster and their respective sizes. Unfortunately, there's a lot of drawbacks since we have to install and successfully run each program, code, or algorithm before being able to extract data. But this is a good point to talk about the future and how to proceed. So here we are with an image of a galaxy and the identified stars in the galaxy. The next step would be to create a circular aperture image of these star clusters, as said in the previous slide. And we would crop our images so that we can get clusters that are within a reasonable range of each dwarf galaxy. This helps us get a better idea on the age and the mass of the dwarf galaxies. Further data obtained will be compared to other merging dwarf galaxies, non-merging dwarf galaxies, or just regular galaxies by themselves. And with this information, we'll be able to find out a little bit more about the early stages of our own universe. My peers each took a unique pair of merging dwarf galaxies, and each pair is in a different part of the merging process. Comparing data can help lay out what happens during that merging process and how each galaxy is impacted. But with this, I'd like to conclude my presentation and thank Professor Stierwalt for the opportunity, as well as my peers for the help. Thank you very much.